All right. So I think we're live. Yeah, we're going to do this thing. Welcome everyone to another episode of The F Word. Um, as indicated in many of the social posts, I promise you'll probably be offended. Uh, yeah, so today I'm going to talk about some of the work we've been doing in Self over the last year. Since I owe you guys tons of updates. On how we're using object-oriented Fortran, as well as some bits in CMake to support GPU acceleration as an optional feature. Let's go ahead and get started. I'm gonna give you some. I want to lay the ground here for like why in the heck we're looking at this. Self, if you're new to this, it's the Spectral Element Library in Fortran. This is a library of Fortran classes to help you easily build spectrally accurate conservation loss solvers. We want you to be able to do this on your laptop, on your desktop, on multi-core systems, on AMD and Nvidia GPU accelerated systems, on accelerated processing units like the MI300A or the GH200, as well as supercomputing clusters. That's a broad reach, but this is the kind of a typical thing that at least folks in Department of Energy and at other at universities they want to be able to do with their applications for research, with the idea that researchers are just going to have a mixed bag of computing facilities available to them. So we want to make sure we can hit all of those as well. These are some of what I would call our self-imposed design criteria, so things that come from wanting to achieve those goals. We recognize that not everyone has a GPU or an APU. Particularly the APUs are very expensive and they're brand new to the market, so there's not very many people who have them. GPUs, again, not everyone has those at their facility. So out of the gates, we know that the library itself should not have a hard requirement to have the tools necessary to offload the GPUs. So we want to make that optional. Not everyone has a specific GPU. Since the last round of DOE procurements, AMD GPUs have been becoming more popular. But there's still a large number of people who have not adopted AMD GPUs, so we want to be able to support both AMD and Nvidia GPUs. I did have someone ask me, well, what about Intel GPUs? And I said, yeah, what about them? Okay, to be honest, I haven't found too many people who are running on them in practice, and even the person who asked me did not have an Intel GPU. So if you guys want Intel GPUs, let me know. I'd be happy to look into supporting that. But at any rate, we also want to provide optional multi-threading. I mean, most platforms these days have multiple cores, so it's a good idea to support multi-threading so you can get some kind of decent performance by taking over all the cores available. We do this thanks to the built-in do concurrent inside of Fortran. So as long as you have a compiler that can digest do concurrents, that's very, very simple to do. We want to minimize use of C pre-processing flags. This is just, I guess I have a bad taste in my mouth from working on Fortran codes at Los Alamos and at Space Weather Prediction Center in the past. I've seen some nasty stuff where you have like 1,000 build options and you have pound if defs everywhere, and when you're debugging code, it's very hard to tell what the hell is actually being run at any given time. So we want to minimize that as much as possible, although sometimes it is just a necessary evil that you have to commit, and we just live with it as long as we keep it under control. We do out of the box want to support domain decomposition like as just a core part of the algorithm so that you can easily scale onto clusters and things like that. And so because of that, we do have a hard requirement that you build the application with MPI support in there. So it does have a hard requirement on MPI, but I'll talk about that in a little bit. And the last one is a huge one for us. I read a paper a little bit ago about how Fortran codes are nothing but archaic monoliths that are really purpose-built for one particular thing, and that it's just not possible to create a generic solver like we're doing today in Fortran. Our goal is to set you up with tools to solve a generic conservation law, and we want to do it to where you have minimal coding requirements to make this happen. So let's talk about a little bit what's going on under the hood itself, so you have an idea of like the things that we need to do to make that possible. Everything in self revolves around interpreting a partial differential equation as a conservation law. You have a vector of prognostic variables. We call that S vector. We have a vector of vectors for the conservative flux. So for each prognostic variable, there is a physical vector, so it points in X, Y, and Z space that tells us, the conservative flux for that quantity. And then you have non-conservative source terms. Most everything in self is focused around calculating this guy. Of course, if your source terms have things that involve gradient stuff like that, that can become quite expensive too. But the big gorilla in the room is the calculation of a divergent flux, which we do currently using discontinuous Galerkin, so a weak form of the flux, a discontinuous Galerkin method to calculate that flux divergence. When we think about space, so if you want to pose that problem in space, you might have some, and this is just an example of a 2D geometry in the background. That would be our physical domain. That domain is broken into elements. Now in self, everything is, so in 1D, it's line segments. In 2D, you do a tensor product of line segments, you get logical quadrilaterals. And then in 3D, we have hexahedra. So yeah, your physical domain's broken into lines in 1D, quads in 2D, or hexes in 3D. And then each of those elements, they can have curved sides and all that stuff, so you can conform to your boundaries using an isoparametric representation. All that means is we're just using high-order polynomials to represent our boundaries. Those can get mapped those all get mapped to a computational domain. So in addition to tracking all the unstructured mesh information, we also track metric terms for each element, so you can do some pretty complicated stuff. Now, with all that in mind, this is how I'm going to walk you through, sort of from bottom to top here, the foundational layers of self. This is a sort of I would say, a mental model for how the source code in self is laid out. So down at the bottom here, we have what I call the foundation, which everything in self is built on the idea of a Lagrange interpolating polynomial. And those Lagrange interpolating polynomials go through specific quadrature points. These are typically Gauss-type quadrature, but we do have support for Chebyshev quadrature, Legendre-Gauss, and Legendre-Gauss-Labato. Okay, so that's basically everything at the bottom. The Lagrange class itself stores a number of pre-built matrices. So once you choose the quadrature, it builds matrices for calculating derivatives, for doing interpolation, for prolonging the data to the boundaries. It constructs what's called a DG derivative matrix. It's the derivative matrix that you get if you do a weak formulation. All that stuff is baked into the Lagrange class. And then you have data, and let me scooch out of the way here. Our data classes, so we have scalars, vectors, and matrices, but we call them tensors. These are mathematical scalars, mathematical vectors, and tensors. And each one of those are endowed with procedures to do interpolation and differentiation operations. And you can imagine differentiation. You have 1D is just derivative. But in 2D and 3D, you have options for divergence, gradient, and curl. And then for the divergence and gradients particularly, we have strong and weak formulations of each of those. All this is done in computational space at this point, so there's no mapping down at this bottom level. What you really need to do things in physical space is geometry, and that's what's up on the next layer above. We actually use those scalar and vector and tensor classes to store physical positions as a function of the computational coordinates. So like, for example, the SEM quad class, we have X and Y values at each of the quadrature points, and then we can take a gradient of the physical position vector, X comma Y, with respect to each of the computational coordinates, and you can get out the covariant and contravariant basis vectors from various operations built on top of that. So yeah, so we basically use the data classes to help us describe geometry. And then the mesh 1D, 2D, 3D classes are what are used to actually store the corner node vertices of your elements, the element to edge connectivity, the vertex to edge connectivity, the edge to face connectivity, etc., so that you can do data exchanges between neighboring elements. So that you can actually do, weak formulation. You can calculate surface fluxes of momentum, heat, energy, whatever your problem demands. Okay, so we have interpolants. We can do things spectrally. We have data where we can calculate things in computational space. Now we have a way to describe space using an unstructured mesh with isoparametric geometry. If we go up above that, we have on the left side here, on that third level up, is what Self calls mapped data. So this is really just a type extension of the data classes that overrides divergence, gradient, and curl operations so that you can compute divergence, gradient, and curl in physical space. So there's some fancy stuff. We have a popular video that we put out a couple years ago on differential geometry. I'll make sure I drop a link in the description when I update this live stream afterwards. But the basic idea is you can write the divergence or gradients in terms of the contravariant, covariant basis vectors, as well as derivatives of your scalars, your vectors and tensors in computational space. But basically the map data, when you think of that, basically this gets you to a point where you can calculate all of these derivative operations in physical space using the geometry and the mesh information. This is also where we store classes to do side exchanges. And what I mean by a side exchange, if I go back to my mesh picture here, like in this little zoomed in portion here, this element on the left is shares an edge with this element on the right. And if I were to compute momentum fluxes between these, I need to know who's neighbor. And I need to be able to share the information in the correct orientation on those edges. That's all handled inside of that map data class. And what's nice is that it allows us to hide all the MPI stuff inside of that so that you never really have to worry about it. All of that's taken care of for you down below. And now we can do sophisticated stuff. Now that I can do divergence, gradient, curl operations in physical space, I can describe my geometry. Now I can create models. And the model class is where we start to build in a lot of template stuff for you. Again, so you don't have to, but because it's OO Fortran, you can always override things and try out really bizarre stuff once you become a self-expert. In the model class, we have a number of time integrators that are built in by default, and that's stored in model. And we have generic type. There are deferred procedures in that model class for doing things like the flux divergence pipeline, etc. Now, in each dimension we have, and I realize there's a typo here, but we have DG model 1D, there's DG model 2D, and DG model 3D. In each of those, we have standardized pipelines for going through and calculating flux divergence, as well as filling in the source terms, so that ultimately when you want to build your model, all you have to provide me is very, very simple, pure Fortran functions that take in the solution state and the solution state gradient and spit out like the flux, the Riemann flux, etc. So we'll take a look at that when we look at code here in a minute. So yeah, like I said, once you get into the like actual specific model development stage, on the top of all of this in Self, you just use pure functions to fairly fill in a few key things. There's only three that are, or I would say really two that are required: a volume flux and a surface flux. That's it. If you wanted to just do that, you can. We do have other things to like make file IO nice, like you can name your variables, you can assign units to them, give them descriptions, so when the HDF5 files are written, all that stuff's encoded in there, so it makes it nice for post-processing and stuff like that. All right, let's talk about optional support for GPUs. So I just gave you like a high level of like, okay, what are the bits that are needed to make this happen? I still haven't talked about optional GPUs yet, but here we go. Every one of the base classes that define each of these things are stored in the source directory. And you'll notice if you look through the source code, as we will here in a few minutes, all of those files have a subscript T at the end, and the classes inside of them have a subscript T at the very end of them. These form like the base of everything. And these classes really implement the CPU-only version. They have the do concurrence in there, so this is what's really providing all that stuff out of the box for running on the most basic hardware. We do have methods for when you do run on GPUs called update device and update host, so that it moves data around very easily through that API. But for, of course, the CPU only side, we just leave those empty because update device, update host on a CPU only platform should do nothing. When we do extensions specifically for CPU, really there's nothing to be done. We just do a type extension and remove the T subscript from the child class, and there's no overridden procedures. So in other words, we inherit everything from the base class. So this is confusing. Again, when we look at the code, you'll see what I mean. Now, if I want to do a type extension of those base classes for a GPU, what's really cool here is I do the same thing as I did for CPU. So I do a new class. So if I had DG model 1DT, I would make my type extension called DG model 1D. I would override the methods that I want to override with the GPU. And for us, we use a lot of HIP. We have some handwritten HIP or CUDA kernels, and in some instances, we've written wrappers around HIP-BLAS or cuBLAS, where we found it's actually beneficial for our performance to do so. We also add additional attributes to these classes for any object that needs to be on the GPU. And now, the way we do everything is all of our HIP kernels are actually written in C. Or our CUDA kernels are written in C, and the wrappers for calling those or launching those kernels are exposed through ISOC binding. So we need type C pointers to be able to interact with the GPU, hence the type C pointer for all of our device data. And then we override the update device, update host type bound procedures so that we actually do the data moves when you're building for a GPU. Now, accelerated processing units like the MI300A are a little bit different. The accelerated processing units have both GPU cores and CPU cores on the same chip, and they share HBM memory. So you actually do not need the additional C pointer. You can pass a Fortran pointer straight into the HIP or CUDA kernels. Of course, you need to pass it as a C through CLOC first to get the C pointer of the Fortran pointer. But we also don't need update device, update host, because the memory between CPU and GPU cores on an APU are the same. So that's the main distinction there. So basically, if you go to an APU, you're just not paying any memcopy costs at all, and you get the benefits of GPU acceleration. So we have a new system coming online sometime next week. The MI300A is getting shipped to our shop. Should be here on Tuesday. So we're quite excited to get this part actually tested. We've been preparing for this for some time, and so we'll see what we learn along the way. Before we look at code, I have to make a plug. There's a few ways you can support this project. Of course, if you want to chat with me now, you can subscribe to the channel, drop your messages in the chat, and I'm happy to answer your questions as we go. We are looking for collaborators that can help support this project. If you check us out on Open Collective, this QR code will bring you there. You can become a collaborator just for $50 a month. Or if you want to be an innovator and actually get access to our MI300 system, that is one way to do it. And you get expert support from us for doing your own conservation laws. Anyways, let's look at some damn code already. Let me go ahead and pull up the VS Code window here. I'm just going to walk you through a few of the classes, again, just to illustrate what I mean here about how we're doing the type extensions. And I will walk through the CMake side of this as well. Please, 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 if you have questions, go ahead and drop them in the chat as we're going. So what I want to look at is, let's see, maybe let's look at a scalar 2D. These guys are interesting enough. So the scalar 2D, so again, I'm in the source directory here, which has all those base classes defined where we have that object. So in self, because we do things with discontinuous Galerkin, we need to have a few different views of our data. So we have what we call the interior points. So these are things at the quadrature points inside of each element. Now the dimension ordering is in 2D we have 2 dimensions for quadrature. So in the I, J directions. Then we have a dimension for the elements you're in, and then we do stack multiple variables inside of this. So like if I'm doing shallow water equations, for example, you might have 3 variables, one for U, one for V, one for the free surface height. Now for the boundaries, we have a quadrature dimension is first, and then we have the boundary ID. So since we're logically squares, the second dimension is 4. So south, east, north, and west. And again, element and variable. And then we have some placeholder attributes, one for my neighbor's value. So if I have an element who shares an edge with another element, I want to know what my neighbor's value is so I can compute Riemann fluxes. So we have those. That's primarily what's used in the side exchange. We have the average of the boundaries, which is typically used for gradient calculations using a Bassi-Rebay method. And then I'm not sure why this is in the scalar class. Should be a vector. I got some cleanup to do, I guess. But at least for our vector 2D, we have a boundary normal. So when you calculate a Riemann flux, that's in there as well. But at any rate, these are the objects here. And then as you see, we have a few different procedures. If you look through each of the files, they're going to look very similar in terms of the API. We always have a boundary interp, so a way to go from quadrature points to boundary points. So basically maps the interior values to the boundary values. Averaging size, which is just going to take an average of boundary and external boundary. Grid interp, if you want to interpolate from one grid to another. And then for scalars, we have gradients, right? But yeah, everything you'll notice has this subscript T. If we look at some of the methods in here, you'll see our do concurrence. Basically, all the do loops are tightly nested loops for everything. You loop over variables, you loop over elements, you loop over quadrature points, and you do a bunch of stuff. That's pretty much how most of the Spectral Element stuff is written, which again is why it's great to put on the GPU. So when I go to concretize this guy for a CPU, the thing that someone's going to end up using here would be the the scalar 2D class. You know, unless you're developing stuff in self, you're probably not going to use scalar 2DT. What you end up using is self scalar 2D. And this guy is just, again, a very, very simple, lightweight extension that is called scalar 2D, so it doesn't have the T subscript, and it labels the backend as a CPU. If I go in the GPU subdirectory, however, underneath there, what we have is backend is GPU. We have a handle for working with BLAS, for hip BLAS or cuBLAS. And then we have some C pointer arrays that are needed for doing all the GPU kernel stuff we have. Most of them are just copies of each of the CPU side attributes. So we have interior boundary, boundary normal, external boundary, average boundary. There's also, sometimes you'll see these work arrays appear up because they're just needed to interface with BLAS in a memory efficient way, etc. And then you see we've also overridden each one of these methods. So, okay, so now I've got this problem, right? You might see now, okay, I've got a source with a self scalar 2DT. I've got a CPU directory and a GPU directory, and they define the same class. So what the heck's going on? In our CMake file, in CMake list, we have, let's start at the top here. There are a number of build options, and we're going to focus on the self-enable GPU. If this is turned to an on state, by default it's off. So we're not going to assume that you have a GPU to begin with, but if you turn self-enabled GPU to on, that is what it's going to do is during the build process, it's going to conditionally select the GPU subdirectory under the source directory. Where that magic happens is inside of the source CMake list. It's nothing fancy. It's just conditionals. If self-enabled GPU, then we set the Fortran source code to the source directory and then we point to the GPU subdirectory. And we also need to add in our CPP files. Otherwise, if self-enabled GPU is off, then the backend Fortran source code is found in the CPU subdirectory. So nothing fancy there, but you needed to know how this kind of comes together. But with this kind of structure, what's also nice, because we don't have a bunch of pound if defs running around, we don't really have too many problems with looking at code coverage reports. The CPU and GPU subdirectories are still counted towards the coverage together. So like when we run tests, we do have builds for GPU being on, GPU being off, and we do test at least on the GitHub hosted actions. All that stuff is CPU only, and then we have some stuff built in for testing on our clusters in house, and then throwing the results back to GitHub. But that's kind of the gist of how it works. Let me to kind of clear up a little bit what I meant about these pure functions. I wanted just to kind of go back over, if you didn't happen to catch the burgers 1D shockwave stuff we did last week, I'll share with you some of the stuff we've got going on in Euler for the linear Euler class at the moment. And I'll walk through, I guess what I should do is let me start with the model first, for the linear Euler model first, and then I'll show you kind of how things end up working. It will go further down into the model class, but I don't want to go too deep. So let me go in the source directory. So yeah, if you want to build your own model, you can. We are working on having pre-canned models so that you don't even have to do that. Like I mentioned last time, we did Burgers 1D, so we have Burgers 1D. We're working on linear and nonlinear Euler equations. Garrett's working on shallow water. If there are other models you want to see, drop them in the chat or leave a comment below the video. Tell us what models you want to see. Anyways, I'll stop rambling. Let me pull up the Euler. So self-linear Euler 2D. We'll kind of walk through this from top to bottom. The linear Euler 2D, basically, you could see here, it's a type extension of the DG model 2D class, which again is a template class that if you just use DG model 2D, the flux terms are 0, the source terms are 0, so if you forward step that model, you get zeros. Nothing crazy. But if we do a type extension of this, you can of course make your model. So here we have linear, again, we're starting with the linear Euler 2D _T because we need to put in type extensions in the CPU and GPU subdirectories accordingly. For Euler, there are some specific things you need. If you're not familiar with this, you need a reference density. So here we're assuming there's no moving background. It's just a static background flow and a constant density. We need a sound speed. I am working on adding gravity to it so we can do things like hydrostatic adjustment, all that fun stuff, which is great for teaching. Now, I filled in more things than you probably need, but the first one here is the set the number of variables. So for Euler equations, we have what do we call density? We have velocity, so U and V, and we have pressure. So that's 4 variables. This is a simple function, so set number of variables. It just needs to take in that class as an input and return it as an output. We just set the number of variables to 4. Great. Now we could set metadata so we can label those objects. Set metadata. Okay, so we have density, rho. You can, despite what you may think, what others may have told you, you can use fancy Unicode stuff. I'm sure it's not perfect. If you find it offensive, you should tell me. I love to hear when I'm offending. Right, we got our U velocity, V velocity, and our pressure. Entropy, yeah, so there's some built-in stuff to track stability of your code if you provide an entropy function. By entropy, I mean mathematical entropy. So it should be a sign-definite function of your prognostic variables. Typically, if you're doing physical modeling, it's typically the total energy of your system. for nonlinear Euler. I've seen folks use the actual thermodynamic entropy as the entropy variable. That's fine too. For this one, we just use a sum of the kinetic energy and the internal energy, the linearized internal energy. Again, all this stuff is going to be in the docs, but you could see here we got 1/2 u squared plus v squared multiplied by rho naught, and then p naught or p squared on this rho naught c squared. Okay, so we have an entropy function. You notice there's no do loops in any of this because you don't really need to be thinking about how we as the self-developers have structured the memory layout. You could see in every single one of these functions, you have your solution variable coming in, and you're calculating a thing at a single point. All the looping and all that stuff is handled in the background by the rest of self. So when I get to, I'll talk about boundary conditions in a minute. Let's go to the flux, and then I'll go back to the boundary conditions. The flux is, again, it's going to take in the solution array. So you have the list of solution variables you have, and then you have the solution gradient at a point, and we're going to return the flux at a point. The way this is ordered is the first dimension is going to be the physical space direction. So, the second dimension is the physical space direction. So 1 and 2. So the outer guy here is this is the x direction, y direction for the first variable. So x direction, first variable, y direction, first variable. So for density, x flux, y flux. The next one is for the u velocity, x and y direction, etc., etc. And so we just, you fill this in for your conservation law, and then the surface flux, which is what we call the Riemann flux, you could fill in. Again, you're going to take in for the Riemann flux, slightly different API, but you have a state on one side of the edge and a state on the other side. So that's SL and SR, and then you have the average gradients at that boundary point, and then you have a boundary normal vector as a unit normal vector. And then with that, usually for every problem I've encountered, that is sufficient information to be able to calculate the Riemann flux. And so you can fill in whatever Riemann flux you want. For our linear Euler 2D, we're just using an upwind Lax-Friedrichs, where the max eigenvalue for the dissipative term is taken as the sound speed. Nothing crazy there. Now, there is an array of boundary condition, like built-in boundary condition options for you to fill in, and I've got tons to still figure out how we're gonna like document and share with you how to do this. But there's a set of boundary conditions that we support out of the box. No normal flow, radiation boundary conditions, and prescribed boundary conditions are supported out of the box. And I believe I can't remember if it's in the main branch yet, but we do have generic boundary condition 1, generic boundary condition 2 and 3. So if you wanted to put in your own boundary conditions and map them to like an integer ID in your mesh files, you can do that. But again, there's so much that's like an active area of development right now. We're working through how to like make that clean and easy. But at least no normal flow, radiation prescribed are set, and we've got those working pretty well. The way these boundary conditions are labeled is you always have the type of boundary condition, and in self we see the fluxes as either hyperbolic or parabolic. The hyperbolic fluxes typically are functions of the solution, and the parabolic fluxes are functions of the gradients. So if you see HBC 2D, that means hyperbolic boundary condition in 2D. And then you have an underscore, and then you have the type of boundary condition we're doing. So we're going to override the procedure for the hyperbolic boundary condition in 2D for no normal flow. And we're going to map that to the one defined for this class. So if you go down here, this is where you see I've implemented it. The no normal flow, essentially all it's doing is setting the external state so that the external normal component of the velocity is negative the internal normal velocity. The tangent component is prolonged, and the pressure and density are prolonged. That gives you a reflecting wave boundary condition. Now, if you ever wanted to know what is the full list of boundary conditions I can override from my model that are supported, if you go to the self model class, up on the top, the self model class, and you can find this in the API documentation too on our site. I'll pull that up here, I guess, in a minute. But the model class provides in its procedure list all the things you can override. So you can see we have HBC 1D, HBC 2D, and HBC 3D. And you have prescribed radiation and no normal flow. So yeah, I guess I don't have the generics in the main class, in the main branch yet. But anyways, those are the three we have at the moment. You can override any one of those for your model to specify specific boundary conditions. There's you'll notice that there is like a sort of a template for the prescribed model and a template for radiation normal flow. The main difference is that a prescribed boundary condition takes in the solution state and it takes in position and time. The radiation normal flow, they don't give a F about position and time. They only care about the solution states. That's the main difference between prescribed radiation normal flow. Okay. Let's go back to our model. So this right here is all that I needed to do to create a linear Euler solver. In the next couple of weeks, I'll be showing some demos with this guy. We'll put in our nonlinear stuff, and then we'll start doing turbulence closure schemes and all those fancy things. And that's where the fun is. That's where the science is. That's where the research is happening. You guys don't need to be thinking about how in the heck am I going to run on a GPU. Now, right now, if I look at the concretizations for CPU and GPU for the linear Euler, they're the same. Okay. They just do a very, very simple, would you call this opaque or translucent? I don't know. A very, very simple type extension with no overridden procedure. So if I run on CPU and GPU, they're identical. How the heck is that possible? Let me clue you in, because there is no free lunch. Let's go to the DG Model 2D class, because there are some important things to understand here. DG Model 2D. The main, actually, you know what? Let me go to the model class. I'll go one step back, and then we'll work our way closer. The main thing that moves the model forward is this forward step method. All right, everything right now we do is explicit time integration. I have got so many things on my friggin' to-do list. Our time integrator loop. This is the template for doing everything itself. When you call forward step, it's going to call this time integrator. It's going to write the model. Tech plot is going to start being deprecated because we're working on some ways to do visualization a little bit cleaner. It increments an IO counter, and then it calculates and reports the entropy to screen for stability tracking. Now this % time integrator. Okay, let's go take a look at that guy. Let's go to the top one. That is a procedure pointer that fits a particular template, the self time integrator template, and we provided a few out of the box for you. But yeah, this is the template that if you want to implement your own time integrator, it just has to fit this subroutine template. So if you write your own time integrator that takes in a model type and it takes in the end time you want to go to, you can write your own time integrator and then use the procedure pointer to point to that new time integrator. If you want us to support it, you can submit that to us and we would add it in so everyone else can enjoy that. So yeah, we have an Euler time integrator. We have low storage RK2 through 4. Let's take a look at Euler just because it's the most simple to take a peek at. So you can see like what happens inside of the time integrator. Basically, it's going to do this calculate tendency and then update the solution, right? Nothing fancy, at least it doesn't seem. So if we do that, let's see. What we need to know is how are we calculating tendency? What is that? What is this guy? I'm just trying to help you guys figure out how you can navigate this code a bit. I hope you find it useful. Look at this. In the model class, it's a deferred procedure. So this is where we start to build in things that are specific to whether you're doing stuff in 1D, 2D, or 3D. So let's take a look at 2D. There's our calculate tendency again. It's no longer deferred at this level. This is that pipeline I was talking about that we give you. You can override this anytime you want, but again, you don't have to. The way the calculate tendency works is it assumes you have a solution at all the quadrature points that's valid, It'll prolong the solution to the element boundaries. It'll take care of doing side exchange for you. So now those boundary and ext boundary attributes are filled in. If you want to do anything else before setting boundary conditions, you can override this pre-tendency procedure and fill in anything else you might want to. The next thing it's going to do is it's going to set the boundary conditions. If the gradient's enabled, it's going to go through and calculate the average sides. It's going to do a weak form of the gradient using Bassey-Rebay method. And then it's going to then average the sides of the gradient so that you can calculate the Riemann flux, the parabolic part of the Riemann flux. Then it calls the source method. So remember, our conservation laws consist of defining a conservative flux and a non-conservative source term. You could fill this guy in, and then we have boundary flux and flux method. Now these guys, let's take a look at, for example, set boundary condition. Okay. Oh, I have case sensitive stuff turned on. I need to get better about that. This, again, this is stuff you don't need to know if you're implementing stuff in the end, but it's helpful to understand what's happening under the hood. What this is doing, it's going to loop over all the elements. It's going to loop over each side of the element, and it's going to use the mesh connectivity information to figure out, am I on a boundary, on a physical boundary? So do I have a neighboring element or not? If I don't have a neighboring element, I'm on a boundary. And I'm also going to grab the boundary condition ID. And this is where we have those built-in IDs for you. So here's our prescribed boundaries, radiation, no normal flow, and right now, nothing else. But those are the three options. If it's prescribed, it's going to call HBC 2D prescribed. If it's radiation, it's going to call HBC 2D radiation. Normal flow, it's going to call HBC 2D normal flow. So hopefully now you can see that, like, if you overrode those specific functions, which are, again, pure Fortran functions that take in the solution at a fixed point and return the external state at a fixed point, that's all you need to really define. The problem with this is you can see right out of the gates, if I do this on the GPU, with just a pure function, what's going to end up needing to happen is I'm going to have to run this part on the CPU and copy data back and forth. You'll still get a correct answer, and for 2D and 3D problems that are big enough, you still get some speed up, but there's a little extra work you can do to make it even faster, and that's the kind of stuff that we love doing. So you shouldn't have to fret about it. And once you have a CPU only model defined and you running it on the GPU and it gets the right answer still, we can help you write the HIP or CUDA kernels from there. But I want to show you what happens when we do the GPU overloading for self DG model 2D. Okay. So again, we do a type extension of that base class, which runs on the CPU. And here you can see we're overriding it on the GPU side. So on the GPU, what we're doing is a mem copy from the GPU memory to the CPU memory. So we're making sure that the boundary state is consistent between CPU and GPU. And then we do your boundary condition implementation on the CPU, and then we copy back the external boundary to the GPU. That's what's done by default. We're working on some ways to use like C++ templates to make this a little bit easier to write the kernels a little bit easier. But that's just kind of the state it is now. Like I said, you'll still run the majority of the code on the CPU. To be honest, evaluating the flux at each point, evaluating the source terms and the boundary terms at each point is small cost in comparison to actually doing the flux divergence, which will run on the GPU by default. I hope all that makes sense. If it doesn't, drop a comment, leave a message in the chat. You can reach out to us at support@fluidnumerics.com. Any rate, that's kind of how all that's going on there. I've been rambling for like 45 minutes, and I think I've touched on about all the things I wanted to share here. Maybe what I can do is pull up there's a couple things I just want to make a quick plug for. So we'll go to Open Collective because this is how you can support us. So we have a collective called Fluid Numerics Open Source, and underneath that, there's a Spectral Element Library Spectral Element Library and Fortran project. We are looking for people to help keep this project funded, because right now we are just doing this out of the kindness of our heart, and then what little time we have in between servicing our customers and keeping them happy. But we want to be spending more time on this. We love that you guys are here. That, like, even just showing up to these is a huge way to support us. We love having you guys around. Please subscribe to the channel if you haven't done so already, and if you really want to become a collaborator, there's lots of nice benefits. We're putting out vetted Docker container images. If you're on Google Cloud, you'll also get access to virtual machine images as well as Terraform infrastructure as code to deploy complete working systems to get self-running on GCP, even on GPUs or CPU platforms. If you go to the innovator tier, if you do have that kind of money, we'll give you access to the same exact compute resources we use to develop self. So this is AMD MI210 GPUs, AMD MI300A GPUs coming next week. We have some V100s in-house as well, and we'll make ourselves available anytime you want to chat on a live call, in a Google Meet or a voice call, whatever you want. We really need people to help us out here. So we can keep doing this. I did see a question come across the chat. How did you get started with all of this? I tell Garrett this a lot. At least I've told him a few times. I was in David Kopriva's class at Florida State. Oh my God. 2013, I think. And we did spectral element methods in that class, and self started there. I mean, that's where I built most of the tools from the ground up, really just from doing that class. That has evolved probably 17 different times into the various renditions as I've gotten better at learning the object-oriented Fortran. And I could tell you Spite is a great motivator. I was not too keen on learning yet another language, another programming language. I saw a lot of people going to Julia, and they're like, "Oh yeah, this is the new way to do everything. You can't do such and such with Fortran." Now, I will say, there's an impressive project in Julia called the Trixie framework. I would say it's a bit more flexible than what we currently have. Like, they can do AMR and all these fancy things with Julia, but it does the same sort of pattern that we have. But I like to think that in some degree Spite motivated me to say, no, well, we can actually make a generic solver in Fortran. So yeah, I don't know. I just love doing this stuff. But yeah, it started from graduate class in spectral element methods, and I just kind of fell in love with it with doing all this. So I also like just seeing other people use code that I've created. It makes me feel good, and I'm sure a lot of people out there feel the same way. It's just nice to feel useful. But yeah, I don't know if I have anything. Maybe I'll just. Was there anything on the GitHub site that I maybe forgot about? Let me. Oh yeah, FEQ parse is another project we do. Yeah, I guess. Okay, so other ways you can support us: give us a star on give us a star on GitHub. Subscribe to our channel. Give me a like. Give me a star on GitHub. Support us on Open Collective. Again, you can reach out, support@fluidnumerics.com. I love answering emails. I'm happy to do a listener email sort of thing here at some point if we get enough. Let's see here. I love Fortran personally. Did my PhD integrating various multiphysics with NEC 5000. Oh, yes, I'm familiar with NEC 5000. Actually, when I was working at Los Alamos, I was doing the OpenACC hackathons, and I did some work with I spent a couple days with Paul Fisher and them when they were migrating to OpenACC. I think he was NEC 5000. Is that right? Would love to do something similar to what you've done. Oh man, dude, thank you. It's very nice of you. Yeah, like there's a lot of great spectral element codes out there, and to be fair to the person that irked me with their paper, I guess the people that irked me with their paper, that is what people were doing with Fortran is writing very specific codes, like, oh, I'm gonna do a compressible Euler solver, and that's all it's gonna do. That's just what people were doing. It didn't mean Fortran couldn't do it. It's just that's what people were doing. And it's very unfortunate that those two ideas have gotten conflated, that because that's what people were doing, that is what it's limited to. And that's just not true. I also, man, the number of times I've been laughed out of a room because I've said, oh, people still program Fortran. In fact, the majority of Department of Energy, Department of Defense codes are Fortran. People think I'm crazy, but I think those who don't think I'm crazy know the real story. But I don't know. I don't know. I've been wrong before, but I don't know. My observations have steered me another direction. Just about every project I've gotten into in the national labs and in any government agency has been Fortran. So, um, anyways, I'll hang around here just for a couple more minutes. If you guys have any other questions, man, it's been so great doing this. I do have another live stream coming up next week. It's not self-related. I need to build up a couple more things in self to prepare for the next one. So in 2 weeks, I'll be back with the F word. But next week, if you're interested in particle and cell methods, we've got another project going on with Geomar and the University of Utrecht. We're putting in support for pushing particles in this code called ocean parcels. We're going to be pushing those around on unstructured grids. So I've been doing a lot of digging into like various ways of doing that. Been a lot of fun learning. So I'm going to be sharing next Thursday. What I've learned so far. So if you're interested in particle and cell methods on unstructured grids, join me next Thursday. And then in 2 weeks, I'll be back with another F word. So I see a question, is Open Collective shutting down this year? If so, are you moving the support to another website? There are ways to do this. I mean, I've thought about how I can put, like, I think the biggest benefit I see to Open Collective is the fact that there's a public ledger, so you guys know I'm spending any money that's donated on this specific project. So, you know, I would like a third-party way of doing that. We may end up just having an integration with our, so if you want to know how the sausage is made, we have a Squarespace site, so I think I can do stuff there, and then I can turn around and publish a ledger about the expenses specifically for the self project. Yeah, it's on my mind. I'm not, you know, too excited about that, but yeah, we'll figure something out. If that is something that's turning you off from sponsoring, I perhaps probably should get a move on getting that organized to move that over. Yeah, so still widely used. Yeah, Fortran still widely used in CFD science and research. I'm jealous of the national labs you have in the U.S. Isn't anything quite like that here in the... Oh, cool. So yeah, you're joining from the U.K. Thanks for coming, man. Yeah, I don't know. Yeah, the national labs are cool. There's a lot of exciting, fun things going on at the labs. I hope you're finding good things to do. If shoot, man, I'd love to talk to you more about what kind of projects you're working on. If you want to drop me a line, support@fluidnumerics.com. I'll be happy to chat with you more. I'd love to hear what kind of projects you do have going on, if you're able to talk about them. Suki, you say I did Fortran stuff 30 years back for my PhD in turbulence using vorticity. Nice. My mind still spins. I haven't looked at problems using a vorticity method. I picked up a book and never really got all the way through it. Nice to see Fortran and still alive and meeting Mr. GPU. Oh, thank you. Is that my new name, Mr. GPU? I love it. That's cool. God buddy, interesting. Good luck with everything. Have free playground and server. I'm not sure what that means. Have free playground and server. If you do want access to the servers, of course, the cheap way to get access to our stuff is just to become a self backer. If you're just a generic customer and you want access, we do have another subscription for that. But we're really trying to drive people to support self. So, Jonathan, oh, thanks, JPA. I look forward to that email, man. Definitely send it my way. Do you have a list of good resources for learning to use Fortran for general solvers? I'm using Fortran for the material point method and would like to learn more. Um, I don't know about the material point method. I haven't heard of that. I'd love to. Maybe I'll Google that and educate myself. Or maybe these days we chat GPT things. I guess. I don't know. Um, so if you're looking for general Fortran resources, I highly recommend you check out fortranlang.org. I'll drop that in the chat. Fortran-lang.org. I believe that's. Let me check that link because if I send you a bunk link, that would be stupid. They have a bunch of resources that are documented for getting started with Fortran, and there's also a discourse. I put the wrong thing in. Did I do the? Yeah, fortranlang.org. Um, that is a great place to go to really find everything you want. There is a Fortran Lang discourse where you could go up and ask questions. Everyone there is just super awesome, really supportive of other people doing Fortran. Of course, I'm mistyping. There we go. Fortran Lang discourse.group. Let me go to the head page. It's just a nice online forum. It's very active, really cool set of people there. There's a lot of different people that announce like monthly calls, stuff like that. The Fortran Standards Committee will provide updates on like new things that are coming in Fortran. There's plenty of good books that are referenced. Actually, one of the guys who's on there quite often, Milan Kurik. I'm sorry if I pronounced his last name wrong. But he's at the University of Miami, I believe, and he wrote a really good book on modern Fortran. In terms of specific algorithms, I mean that's going to be domain science specific. At least for Spectral Element, I found David Kopriva and some of the people who he had worked with have books out there, and they just put what I would call pseudocode in those books, and that's really the pseudocode is what we then translate to the whatever specific language we're using. So like in our case, like I said, there's Trixie, which basically does a lot of the stuff that's in David Kopriva's book. Plus they have like entropy conserving methods, which is more stuff documented in literature, and it's currently not in a book form at the moment. I'm certain they're working on a book. But a lot of times the domain scientists will just kind of like work through that stuff and put out pseudocode, and then you just translate it into Fortran syntax. So you kind of need to have knowledge of both. Generally, if you're looking for like generic, solvers, there's numerical recipes in Fortran. That's just like a big black cookbook that you can do. They have numerical recipes in C, C++, but it's the same content, just different language. That's another route to go if you're just looking for a lot of generic stuff. John, I hope that answered your question. If you guys have anything else, let me know. But I think yeah, check out the GitHub. That's github.com fluid numerics self. We are very actively trying to add new models there. We've got documentation coming. If you like what we're doing, give us a star. Subscribe to the channel. Support us on Open Collective or wherever we're going to be in the future, receiving funds, those kinds of things. If you are a researcher, I would say about 50% of our income as a company comes from doing basic research. We do have a separate pricing schedule for doing basic research than what we have for the commercial side. Typically, it's just basically direct cost plus overhead. U.S. based customers, we are set up on SAM.gov. We have done NSF projects in the past. So if you were looking to do a problem and you're interested in using spectral element methods, definitely reach out to us. We're happy to be co-collaborator, co-PI. We can help with proposal development, all that fun stuff. So any way that justifies us spending more time on self, that's what we want to be doing. God buddy. I'm building a home lab out of old Xeon Phis. Yes. Love it. Do that Beowulf cluster, man. Ready for Xmas. Oh man, I hope Santa treats you well and brings you all the Xeon Phis that you want. If you happen to get an Iris Xe GPU and you want me to support it, you should open an issue on our GitHub, and I'm happy to look into it. I just need to figure out how to get a hold of one and get it set up in our site, I guess, or if I can get access to one, I suppose. John, thank you for the information, all the hard work, or all the work. Hope Hurricane. Oh, dude, yeah, we were like 30 minutes east of like Disaster City for Helene, but thank you. We got really lucky. Well, cool guys. I'm about cooked for the day. But I do appreciate you coming in, chatting with me. I love this. Let's keep it going. Again, next week I'll be back with particle pushing on unstructured grids. That'll be just more theoretical particle and cell stuff, and grid searching and interpolation techniques there. And then in 2 weeks we'll be back with another episode of the F Word. Again, if there are models you want to see implemented, things you want to do, please direct us. Tell us what you want to see in Self. We want to get you guys using it and making it easy for you to do research. Thanks for tuning in. We'll see you next week.